I spent a big chunk of my career trying to understand about issues related to uncertainty. A lot of the early part of it was about how markets respond to uncertainty, investors and the like, and how that shows up in prices and everything, and how people cope with it. More recently, I've been moving my interests more towards uncertainty in policy, and that's where I thought I'd be sharing with you some ideas today related to uncertainty in policy, and I'll use climate change as kind of the focal point example, although some of the issues, challenges certainly apply much more generally. I'm interested in this question about how proactive should policies be in the face of uncertainty. One kind of naive response to uncertainty is, well, if we're uncertain, why not just wait and figure things out and not do anything until we got everything sorted out? And that's not always the wise course of action. And so I want to address that issue about how do we really address it, how do we confront the uncertainty in a way that's really prudent, smart, intelligent, and the like. And as economists, we always like to think about trade-offs, right? So in the context of uncertainty, there's two trade-offs that I find interesting. So when we go out and build these models and make forecasts and the like, there's different ways to use them. One is to use them to figure out what's the best guess, what's the best prediction out of that model. Okay? Another one is to try to figure out, well, what's a possible bad outcome coming out of that model, out of those models. And if you look at how models were used coming out of the pandemic, sometimes they're used one way, sometimes the other way. And both uses are of some interest. If you put all your attention on best guesses, then there may be a non-trivial chance that you've kind of missed out some important outcomes. On the other hand, if you spend all your time on just potentially bad outcomes, just give up, don't give up, and don't get up in the morning and just quit. There's nothing to do. So the question is, how do you go in between these two? And that's really one key interest or one key thing that uncertainty can help you think about in intelligent ways. The other one is, do we act now or do we wait until we learn more? Now there's a trade-off there because it may be easier, less costly to act now under the possibility of something bad happening until we wait and we find out. And maybe once we wait and we find out, it's very, very costly to do anything about it. So again, there's a trade-off. And so we have to think about that, yes, more information is good, and so we want to hold off some of our actions until we learn more, but on the other hand, there's reason to want to act now. And both of these are kind of relevant for thinking about climate change in my views. So here's a quote from a recent paper in Nature that I have some sympathy with. The economic consequences of many of the complex risks associated with climate change cannot, however, be quantified. I would say fully quantified, but these unquantified, poorly understood, deeply uncertain risks can and should be included in economic evaluation processes, in economic evaluations. Now, this paper makes a statement, but it doesn't tell you how to do it. I mean, it just says this is something that we ought to be thinking about when we're looking at uncertainty. And so, really, the question is, how do we think about this in a more operational way? How do we kind of figure out how to address these challenges? And I'm going to be backing off this notion of risk, and I'm going to try to think about uncertainty in more general terms. So next, here's something that keeps me up at night. Sometimes. There's other stuff too, but this is one of them. So Hayek was a very, very prominent economist. So when Hayek won the Nobel Prize, he shares it with Myrdal, and I don't think he's too happy about this. So Hayek wins the Nobel Prize in economic sciences, and when you do that, you have to write this essay, and the charge of the essay is you're supposed to explain to the world, kind of why you won this prize, which is at that point in time very boring because it's often research you've done, well off in the past. And so what most people do is maybe spend a little bit of time on that, but then go off and write about something else interesting. So Hayek writes this essay, and it's one of the more interesting essays related to the Nobel Prize. He basically wins the Nobel Prize in economic sciences and challenges the extent to which economics is really a science. And that's really the whole nature of this essay. And he says that mathematics is kind of good as a language of clarity, but quantitative work is just, just not what economics should be about. He thinks econometrics, a field that I have some sympathy with, has accomplished nothing in centuries. So I don't agree with all aspects of this essay, but it's a great one to read. This quote here, however, I have a lot of sympathy with. Even if true scientists should recognize the limits of studying human behavior, as long as the public has expectations, there'll be people who pretend or believe they can do more to meet popular demand than was really in their power. And I think you see this all the time in economics. There's this notion that you have to pretend that you know things with great confidence to have any influence. There's this American president that the younger people here may not know because they weren't born yet. His name was Lyndon Baines Johnson. Okay? And this is a story I learned from one of my longtime collaborators, Buzz Brock. Lyndon Johnson has an economic advisor. He asked him for some advice. I have to give you some context. Lyndon Johnson, before he became a senator, then president, was a cattle farmer. Was a rancher. And so the economic advisor starts telling him something, and then he starts kind of shading his answers. Well, I'm not quite sure at this, and starts saying, that the numbers might be a little bit more fuzzy. Johnson turns to the advisor and said, "Ranges are for cows. Give me the number." That's kind of the sense that we can't fuss around with uncertainty. We just got to tell people answers, and I think that can lead to a certain bias in how we influence policy. And this certainly also shows up in discussions of climate change and again the like. And so I think I would very much like to make conversations at a little bit higher level, so we're able to talk about uncertainty in intelligent ways and not pretend that we know more than we do. Okay. So in our studies of climate change, we like to think about 4 different channels of uncertainty that uncertainty can matter. One is the usual economic notion. When we build economic models, we have some type of technological uncertainty. If we make capital investments today, we're not sure what the returns will be over longer horizons. The next one comes out of geosciences. And so what the geoscientists investigate is, if I emit CO2 into the atmosphere today, what are its implications in terms of the future climate, say temperature? If you look, in our studies, we've looked across predictions across 144 different models, and there's a huge range in terms of what the implications are longer term. And so most of these models will tell you that the emissions today will kind of gradually peak up to about 10 years and then flatten out, and then be roughly permanent. Now here's requires a qualification. For a geoscientist, long term is many, many centuries. For an economist, a few decades. So long term for an economist means that for our purposes, this stuff settles out. There's very, very long term dynamics in which add more complexity to it. Okay, but that's a rough pattern, and these models were kind of all agreeing about that, but the place they would settle out to after 10 years was very, very heterogeneous, and so that's a source of uncertainty. Economics parts of this. If we're going to be changing, warming the environment, that's going to affect economic opportunities. Now, the challenge here is the fact that we're pushing economies into places they haven't really visited in the past. And so, yes, we have this wonderfully data-rich environment, but the data is not rich on all dimensions. It's sparse in some places, and so we can't just look at data and just turn this over to empiricists. So there's an important source of uncertainty here as well. And then the final one, and this is unfortunately left out of a lot of discussions of climate change, but I think it's important, is potential technological solutions. How about we make a research and development invested today may eventually lead to economically viable technologies. Now, potentially the most dramatic of these, and one that's incredibly uncertain, is nuclear fusion. There's been investments made by various different governments, the U.S. government, Japan, Britain, different European consortiums. And and this made some progress, but it's a long ways from being economically viable. I had organized a conference this past spring, and we had a top scholar in this area from Princeton, who's Cowley, and he's giving this interesting talk. He said, it used to be that we would always say that nuclear fusion is 30 years away. Now we say it's 10 years away, therefore we must have made progress. It's still always 10 years, but it's uncertain. It could be a huge advance in terms of addressing climate change technologically, but we're just not sure about if or when it's going to pay off. So these are the types of uncertainties which come into play. And as you can see, if you want to think about this problem, you have to think about uncertainties from sources outside of economics. This is really, there's a bunch of different pieces one can put together. And part of our research has been trying to figure out which of these channels is really most important in terms of designing prudent policy. Okay, so we can think of that, coming out of this, a couple different policy ambitions. And we might want to assess the implications for uncertainty. One is you may want to reduce fossil fuel emissions. There's been lots of attention on that. The other one is you may want to invest in the discovery of new technologies that are clean replacements. Okay, so here in the research that I and others have been doing, we're trying to think about uncertainty in broader terms than is taught in economic classes. That's typically and standard treatments of it. The standard treatments are the so-called risk model. And in economics, risk models are basically coin flips, dice rolls. You know probabilities, but you don't know outcomes. Okay? So lots of the economic models we build, we put people inside our models, and we just pretend they know all the probabilities and the like. And so that's just a pure risk notion. We just don't know outcomes. Another one's ambiguity. So this is one that has been relevant for statistics for a long time. If I've got multiple models on the table, how much weight do I assign to each one? Okay? So one possibility is, well, the data just really tells me so much about the different models that how much weight is not a big deal. But I think in the case of climate change, that's not true. Our historical evidence really doesn't fully settle this issue. So I often like to say the following. St. Thomas Aquinas has this kind of famous quote. The quote is, "Beware the person of one book." Okay? So I've been, in my papers, I've been trying to modify that slightly. Beware the person of one model. If you've got an economist bearing one model, you bet, they may be marketing something that doesn't really recognize the fact there's other possible explanations on the table. So I think it's important to consider these alternative models, but then there's this issue of how much weight you put on each one. So one solution to this was by a famous statistician who did this work at the University of Chicago, actually, Savage. And it was he and in part Di Finetti from Italian developed this notion of subjective probabilities, in which through introspection or the like, wherever we're missing probabilities, we kind of fill them out, and produces that as kind of a smarter, rational approach to things. And that's a beautifully elegant theory. It's kind of the gold standard in decision theory in many respects. But my colleague at Chicago, Stephen Stigler, is an expert in the history of statistics. And he's been digging me out some very interesting quotes and exchanges that Savage himself had, and said that in many sets of circumstances, these subjective inputs, these subjective probabilities can only be known very crudely. And so that's what we're trying to address here. Finally, the models that economists use are wrong. The models that across all disciplines are at some level wrong if you put enough of a microscope at them. They don't explain everything. We think they're useful abstractions. We think they have important insights, but they're not correct. Now, when we teach econometrics, we spend very little time on this subject, but I think it's a very important question in how we use models. So when we use models, we have to recognize, we have to somehow acknowledge that they're not quite right. They're approximations of things, And so how do we account for that type of uncertainty? So once we're thinking about these policy problems, my view is we need to think about them along all these dimensions and not just the risk dimension. I'm just, I can show you a bunch of cool equations with Brownian motions and Poisson jumps and stuff, but I'm going to skip that for today. I could send you some papers, but roughly speaking, a baseline economic model here would start off as following. We have some type of production, okay? So that production produces output. The emissions come from some energy input into production. There's a capital input into production. And from that, and then from that output, I'm going to take some of that output. I'm going to reinvest it into building new capital in the future. I'm going to consume some of it, and then that contributes then to economic well-being. So this is kind of a very stylized characterization of an economic dynamic model. Now, this is a model in which Adam Smith's invisible hand works great. Okay? There's no need for policy intervention here. This is a case where everything's just working right. Okay, so now the climate change introduces this so-called externality, which I guess Purdue made famous, many decades ago, because these emissions at the same time, these energy inputs at the same time are enhancing production, are emitting CO2 into the atmosphere. That damages the climate, and that potentially hinders economic well-being, or alters production, or the like. So this is the part where the invisible hand starts to fail, right? And this is where Purdue's approach to this is to design taxes in order to address this so-called externality. Finally, we might take some of that output, invest it in research and development, develop some new technology in the future, and that gets us out of the need of using dirty technologies. So these are just kind of the ingredients inside the models which we like to look at. So what our initial research does is the following. We look at these different sources of uncertainty. I give you 4 channels: the kind of economic productivity, the geoscientific, mapping from emissions into climate change, the economic one, climate change into economic opportunities, and then finally research, the long-term payoffs in research and development. In our initial calculations, the latter one dominates, and rather substantially so. Now what we also find is this source of uncertainty, the more uncertain you're about this, makes you want to actually do more research and development rather than less. But emissions are also sensitive to uncertainty, but much less so. But you still want to reduce emissions in order to give research and development a much better chance to play out. Okay? And so these are the type of findings which we're getting. Now let me be very clear about a few things here. One is, so far I'm not talking about how to design policies to address this. So there's lots of discussions about carbon taxation, and carbon taxation can certainly get you part of the way, can certainly address the reduction in emissions. Whether it also addresses the research and the need for research and development depends on your views of whether this research and development is something that is external or something that can be internalized by the private sector. Now, if we take the case of nuclear fusion, what's happened there has been that there's been some initial investments by governments, but now it's on the radar screen of venture capitalists. And venture capitalists are getting more and more interested in it. And so my own view of this is that there's some initial, perhaps, government investments needed for the basic science, but as soon as you start establishing economic viability, it should be offloaded to the private sector. I think having our governments be these kind of green venture capitalists in general is not a great idea. And so I think, so the type of research and development we're thinking about are big project R&Ds, like developing the atomic bomb by putting people on the moon, or in this case, say nuclear fusion. Okay, so here's just some Our model has lots of interesting predictions. I'm just going to show you some illustrative paths that come out of our model. This is when we're imposing prudent climate policy. Our models are stochastic, and so there's there's not a single trajectory. There's a whole bunch of different possibilities that come out of it. I'm just going to show you 5 paths just to illustrate the type of behavior, the behavior that comes out of it. So this is what I call robust R&D. This is R&D type differences. And these uncertainty adjustments we're making here, you're almost doubling the amount of R&D you do. And then now, I know what this R&D does is, and the reason why it's so potent here is that it really resolves a big chunk of uncertainty down the road. And so that's why there's such a big payoff to it. But anyway, on this first path, what happens is over 40 years, there's no technological advance yet. This technology is not, the new technology has not come online. There's a second type of big event that we also have. It's in climate economics, in climate sciences, people sometimes talk about tipping points. For us, a tipping point's a little bit different. A tipping point is some type of realization of what the damages are going to be, the climate change at the more extreme outcomes. And so in order to address this trade-off between acting now versus waiting, we have these events, there's a big event in the future triggered by changes in temperature. So anyway, neither of these events has happened yet. Here's what happens, this trajectory. You drop your R&D, and why you drop it? Well, here what happens is you realize in the future damages are just not going to be such a big deal anymore. We feared they might be excessive, but they happen not to be so bad. This one just does the opposite. Right here, you find out that damages are pretty bad. Here you make the research and development discovery. And so once that's made, then there's no reason to invest in this technology anymore. That happens at year 25, and here it happens at year 20. So these are just different possible outcomes that come out of our model. Here's a corresponding temperature behavior. The model's kind of designed so that you never go above a 2-degree anomaly, which is climate scientists speculate about 1.5 and 2 degrees as being critical points. So remember, path 1, we actually get kind of good news about damages. Path 2, we get bad news about damages. Path 3, we make path 3, I'm sorry, I got this wrong. Path 1, there is no news about damages or technology. Path 2 is the case where there's good news. Path 3, there becomes bad news. Path 4, you make a discovery. Path 5, you make a discovery earlier. These are just, these are just examples of trajectories that come out of our modeling under uncertainty. So anyway, the main observation I want to make here is that sometimes the best response to uncertainty is to be more proactive, not more passive. The extensions, the types of uncertainty quantifications we're trying to develop, I think are much more generally applicable. I've been illustrating some of our current work does in the context of climate change, but I think it's much more generally applicable. And I think it's applicable not only to government policy decisions, but more generally to private sector decision making as well. Now, my view of this uncertainty is I think that in the private sector, smart decision makers are kind of intuitively doing some of the stuff that we're trying to formalize already. So I'm not trying to say that we're sticking brand new ideas in their heads. We're all about trying to make it more systematic. And so this research is part of a larger agenda that wants to study the uncertainty impacts of both private sector and public sector decision making.